So areas under a curve and total visitors. So assuming that, let's say the zoo got this new enclosure for these orangutans, over the course of, let's say, 10 days, we noticed the number of visitors grew exponentially. So what does this have to do with area under a curve? Well, basically the area under a curve can allow us to actually calculate the cumulative frequency, so the total number of visitors over this period of 10 days. So in this lesson, we'll be looking at approximating area under a curve. In particular, we'll be focusing area under a curve and using right and left endpoint approximation. One of the main applications of integration, or that is part of this course, is finding the area under a curve. So generally, the area under a curve refers to the space between the function f of x and the x-axis. Later on in this course, we'll be looking at the area between two curves and below or under the axis. But sort of one of the main ideas of this particular lesson is just finding the area underneath the curve and the x-axis. So what does it mean when we approximate? Well, basically, we'll be looking to find what shape or shapes could be used to approximate the area under a particular curve. And in this case, we have a parabola. So we could potentially use rectangles. We could potentially also use a trapezium or a triangle, or if you like, a rectangle and half a circle, sort of geometrical shapes. But in this particular session, we'll be looking at right and endpoint methods. So one of the things I do want to mention is when you are approximating the area under a curve, you want to ensure that you choose an appropriate shape. Otherwise, the estimate will be quite different compared to potentially something that is a little bit more accurate. So right and left endpoint approximation. So right endpoint approximation is the one we're going to start with. So to find the right endpoint approximation, we aim to calculate the sum of the areas of the rectangles with a specified width, generally given in the question, and a height given by the right endpoint of that rectangle. So if we look at the example of f of x equals negative x squared on 4 plus 4, we're going to find the height of the rectangle is always going to be the right-hand side or the right endpoint of these rectangles. So for example, let's say that is x is 1, 2, 3, and 4. So to find the height, we just substitute in the right endpoint. So substitute in 1. So this would be f of 1, f of 2, f of 3, and f of 4. If we look at increasing and decreasing functions, so the first example, negative x squared on 4 plus 4, we'll notice that that function decreases. So as x gets bigger, that's a decreasing function. So for a function that decreases, we can see our approximation, the rectangles, would actually underestimate the area. The reason being is because we have these little gaps that it doesn't count. So essentially it's underestimating when the function is decreasing. Let's take a look at f of x equals x squared on 4. Because this function is increasing, we'll notice that the right endpoint method actually overestimates the area. So we've got these extra bits that actually go beyond the curve. So it's overestimating because we're counting these extra portions as well. So in this example, we're going to be looking at using the right endpoint method of approximation to estimate the area under the graph of f of x over the interval 1 to 5 using rectangles of width 1 unit. So generally speaking, you will be given the width to use. So in this case, we're being given a width of 1 and the interval 1 to 5. So the first thing I want to do is we're using the right endpoint method. So we have to use the right endpoint of our rectangle. So we can see this is an increasing function. So estimate will actually, or overestimate. So therefore we don't count. So therefore this is going to be, because we want to calculate it over the interval of 1, 5, the only rectangles we want is, or it's everything except this left-hand side. So we don't want that because we're being given the interval of 1 to 5. So therefore, to find the approximate area, we're going to have 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4 plus 1 times f of 5. The reason why we have 1 times is because that's our width of 1 unit. F of 2, so we're essentially going to substitute into f of x, so 2 root x plus 1. So it's going to become 2 root 2 plus 1 plus 2 root 3 plus 1 plus 2 root 4 plus 1, and then finally plus 2 root 5 plus 1. Adding this all together, we can't add the surds because they're not like surds. However, you can add the constants, so that you can add the 1. So 1 plus 1 plus 1 plus 1 is 4. So it's going to be 2 root 2 plus 2 root 3 plus 2 root 4, which becomes 2 times 2, so it's 4, plus 2 root 5 plus 4. And then our final solution is therefore 2 root 2 plus 2 root 3 plus 2 root 5 plus 8 units squared. The reason it's units squared is because it's area, so you're approximating the area under a curve. So therefore, unless you're given units, for example, centimeters or meters, if you're not, just leave it as units squared. In this case, I've just left it as an exact value, now using surds. So really what we've done here is we're using the right endpoint of those rectangles. So that's why we're going to essentially overestimate the area for this particular example. So now looking at left endpoint approximation. So to find the left endpoint approximation, we aim to calculate the sum of the areas of the rectangles with their specified width, again would be in the question, and a height given by the left endpoint of that rectangle. So for a function that increases, the left endpoint will now underestimate, because again we have these areas that it doesn't account for. And for a function that decreases, it will overestimate, because it gives us extra piece that is above our function. So in summary, when we want to find the area under a curve, so it refers to the space between f of x and the x-axis over a specified interval. For the right and left endpoint methods, starting with the right, you want to essentially find the right endpoint of that particular rectangle. So let's say, for example, it's between 0 and 1. You'd find f of 1, because that's the right-hand side of that rectangle. If it was the left endpoint method, then you would find the left endpoint of that rectangle. So again, using the example of 0 and 1, you would find f of 0, and then continue on that path over the interval that you have been provided. So remember, increasing and decreasing functions. If the function is increasing over the domain, the left endpoint would underestimate, whereas the right endpoint would overestimate, and the converse is true for when f is a decreasing function. So our next lesson will be looking at approximating the area under a curve, part 2. So again, we come back to this image of the orangutan and the data. So we've looked at the right endpoint and left endpoint. And now, if we were to use those approximations, in some cases, we would either underestimate the total number of visitors or overestimate the total number of visitors to their enclosure. So now we're going to be looking at other ways in which we can potentially approximate the number of visitors to see the orangutans. So in this lesson, we'll be approximating the area under a curve. In particular, we're going to be looking at the trapezoidal estimate as well as comparing estimates. So the trapezoidal estimates, essentially we want to use trapeziums now to estimate the area. So instead of using rectangles, for the trapezoidal estimate, we use trapeziums. So if we think back to our understanding of measurement, the area of a trapezium can be given by a half of a plus b, so the top plus the bottom, times the height. So you might think, how does this actually relate to a graph? So as you can see, we have sort of rotated this trapezium to fit under our curve, and you'll notice it gets quite close to the curve. So it's sort of, more often than not, a better approximation compared to rectangles. So what you will notice is we have B is going to be the left-hand side of your trapezium, A is going to be the right-hand side of your trapezium, and H will always be the width of your trapezium. So again, this will be specified. So the area under a curve can be approximated using the sum of the areas of each trapezium. So if we look at this example of f of x, so it's f of x equals negative root x plus 4. So our first point, that's going to be 0, 4. Our second point, that's going to be 1, 3. Our third point, that's going to be negative root 2, 2, negative root 2 plus 4, 3, negative root 3 plus 4, and so on. So how would we find the sum of these trapeziums? Well, if I was to draw a trapezium over this interval of 0 to 3, so to find the area of each of these trapeziums, so we know this distance is 4, this distance here is 3. So the area of this particular trapezium would be a half of 4 plus 3 times 1. So the times 1 you don't really have to worry about in this case because it's the width of 1. So if you were to just write a half of 4 plus 3, that would be fine, only for as long as obviously the width is 1. Then to find the area of the second trapezium, this would be a half times 3 plus negative root 2 plus 4 times 1, because that's, again, the height is the width of the trapezium. To estimate that, you would have to use a CAS, or you could approximate the square root of 2. To put that all together, now you just add the areas. I want to generalize something for you. So what you'll notice is, if we look at the first trapezium, we have a half of 4 plus 3. So essentially adding the first two y values. So what you could say is, if we look at the sum of the areas, you would just have a half of f of 0 plus f of 1. Then plus a half of f of 1 plus f of 2. Again, times 1. In this case, I won't write it just because we're assuming that it's a width of 1. If it was a width of 2 or 3 or something other than 1, you would just multiply it by that value. Then, in this case, we'd have half of f of 2 plus f of 3. And you can see it keeps on going. So that's another way that you can write your answer to then find your total sum of the area of your trapeziums and hence the area under your curve. So it's a sort of another general way of finding that area. So approximate the area under curve f of x using the trapezoidal estimate with the width of 1 unit. So again, that's been specified, where x is an element of 1 to 4. So we're looking to find the area under the curve between 1 and 4. So that's the first thing I want to find. So this is going to be 1 comma f of 1, and then 2 comma f of 2, 3 comma f of 3, and finally 4 comma f of 4. And then now to evaluate. And from this, we can either do it by hand, or we can do it in our calculator, particularly when we have something like the square root of x and we're trying to find, for example, the square root of 3. We would use our CAS to now evaluate this. But before we do this, I will show the substitution. So we'd have a equals a half. I'm actually just going to take out the factor of a half because it's common to all three sums. So then this could essentially be the same as, before we substitute, actually I might show you this, f of 1 plus 2 times f of 2 plus 2 times f of 3 plus f of 4. So what you'll notice, because the reason why I've multiplied them by 2 is because we have 2 f of 2's, 2 f of 3's. So we can essentially multiply them by 2. So a is equal to a half of, now f of 1, so it's going to be negative root 1, which is just negative 1, plus 4 is 3. Then f of 2 is going to be negative 2 root 2 plus 8, because f of 2 would be negative root 2 plus 4. Timesing that all by 2, you get negative 2 root 2 plus 8. f of 3, you get negative root 3 plus 4. Timesing that by 2, you get negative 2 root 3 plus 8. Then finally, f of 4, substituting of 4, so you get negative root 4, which is going to be negative 2 plus 4 is positive 2. So now to evaluate this in a CAS or any scientific calculator, the area is going to be equal to 7.35 units squared. So that will be your final solution. So 1 to 4, you want to find each of your endpoints. So 1, f of 1, 2, f of 2, 3, f of 3, and 4, f of 4. Substitute in to find the corresponding y values, and then evaluate your final solution. So in this case, as an approximate solution, we'd have 7.35 units squared. So again, we can see even just by the image that using a trapezoidal estimate, we're going to get quite an accurate response compared to either the left or right endpoint estimates. So comparing estimates, what happens when we make the width smaller? So to help us answer this question, let's refer to the previous multiple choice activity. So as we can recall, the estimated area using a width of 1 over the interval 0 to 4 was 21 units squared. So let's find the approximate area using a width of a half over the same interval. So first, let's just refer to the equation. So we had f of x is equal to negative x squared onto plus 8. So now we're doing the same thing, just instead of a width of 1, we're using a width of a half. So we'd have 0, f of 0, a half, f of a half, then 1, f of 1, and so on. So to write this out, I'm going to do that a equals a half times f of 0, then plus 2 times f of a half, plus 2 times f of 1, plus 2 times f of 3 over 2, plus 2 times f of 2, plus 2 times f of 5 over 2, plus 2 times f of 3, plus 2 times f of 7 over 2, plus f of 4. And now we want to multiply this all again by a half. The reason now I've multiplied it all again by a half is because the width is a half. Before, the width was 1, so we essentially multiplied it by 1. But now, because the width is a half, we have to multiply the whole thing by a half. So this doesn't mean that the answer will be 21 on 2, because we have a lot more trapeziums that we have to find the area of. So we're making that sum, and again, you can see it sort of gets, or ideally, if I was a better drawer, those trapeziums should get closer and closer to the curve. So the idea is that the more that we cut our curve into these smaller trapeziums with smaller width, we get closer to an accurate solution and closer to the exact value of the area under a curve. So to evaluate this, we'll then put this into our CAS, because that would take quite a long time to do by hand. So therefore, putting this into the calculator and evaluating all of these values all together, we're finally left with A equals 21, or approximately 21.25 units squared. So again, getting closer to what the exact value would be for this particular graph. So as you may have realized, the smaller the width that you choose to approximate with, the closer you get to the exact area value, and hence the smaller the percentage error or difference. So comparing estimates to exact areas. In some instances, you may be required to find the percentage error or difference between the exact area and the estimated area. This is particularly common sort of application kind of questions, potentially some extended response questions as well. It isn't possible to use an infinite number of rectangles or trapeziums of the smallest possible width, and there may be no shape that fits exactly or fits the curve exactly, excluding linear functions. For example, you could use a right-angled triangle to find that area. So at times, apart from linear functions, there may be a difference between the exact area and your estimate. So to find this, we can use the formula percentage error equals the estimated area minus the exact area divided by the exact area. In some instances, if you generally want to use whatever's bigger. So for example, if the exact area was larger, you'll do the exact area minus the estimated area, then divide by the exact area. But essentially, it's whichever is larger, but you'll always be dividing by the exact area. And then you multiply it by 100% to find your percentage. So the function f of x equals 2 root x plus 1, where x is an element of 1 to 5, has an exact area of 19.91 units squared. Calculate the percentage error using a right endpoint estimate. So using a right endpoint estimate over the interval 1 to 5, so what we can do, we know let's start at 1, so using the right endpoint. So we're going to essentially have at 2, so this is going to be 2, f of 2. So we have 4 rectangles to use. So we're going to calculate our percentage error. Before we can do that, we need to find the estimated area. So we're going to have, where is it? Let's say we're going to have a width of 1 and a height of f of 2. So I'm just going to write f of 2 is equal to 2 root 2 plus 1. F of 3 is equal to 2 root 3 plus 1. F of 4 is equal to 2 root 4 plus 1, which is equal to, the square root of 4 is 2. So 2 times 2 is 4, plus 1 is 5. And finally, f of 5 is equal to just 2 root 5 plus 1. So now putting this all together, the width of each of these rectangles is 1. So therefore, we're going to have area is equal to f of 2 plus f of 3 plus f of 4 plus f of 5, which equals 2 root 2 plus 1, plus 2 root 3 plus 1, plus 5 plus 2 root 5 plus 1, which is equal to 2 root 2 plus 2 root 3 plus 2 root 5 plus 1, 2, 7, 8. So therefore you can't simplify those thirds, so putting into our CAS to get an approximate solution. So this is approximately 17.35. So this is our estimate. 19.91 we know is our exact. So therefore, percentage error is equal to the exact, which is 19.91, minus our estimate of 17.35, divided by the exact, which is 19.91. Don't forget you times 100. So this is approximately 0.129 times 100, which is equal to 13% when rounded to the nearest whole percentage. So again, like you would normally do, find your estimate, in this case using the right endpoint, so you always want to use the right-hand side of the interval that you're working with. So starting at 1, the right-hand, well, you essentially go to the right-hand side of 1, which is 2, and then start from that to f of 2, and then do the same thing, f of 3, f of 4, and so forth, to f of 5. Width is 1, so it's multiplying by 1 again, adding it all together, putting the final solution into your CAS to get an estimate of 17.35, and then you have the exact area, 19.91 minus 17.35, divided by the exact area, times it by 100 to get your final percentage, and we'll just round it to a whole number. So let f of x equal negative x squared on 2 plus 8, where x is an element of 0 to 4. The difference between the right endpoint method of approximation and trapezoidal method is closest to. So I hope that you got the solution A, 4 units squared. Now we'll take a closer look at how we arrive at this solution. So let's first look at the right endpoint method of approximation. So right endpoint from 0 to 4, we're going to be starting at 1. So 1 comma f of 1. Then we have 2 comma f of 2. 3 comma f of 3. And finally 4 comma f of 4. Let's evaluate what they are. So we have f of 1 is equal to negative 1 over 2 plus 8, which is equal to 15 on 2. F of 2 is equal to negative, so it's 2 squared, which is 4 on 2 is 2. So negative 2 plus 8 is 6. F of 3 is equal to negative 9 on 2 plus 8, which is equal to 7 on 2. And finally, f of 4 is equal to 0. So now to find the sum of the areas of those rectangles, we have those. So therefore we have the area is equal to 15 on 2 plus 6 plus 7 on 2 plus 0, which is equal to, so 15 plus 7 is 22, 22 on 2 is 11, so it's 11 plus 6, which is equal to 17 units squared. Now let's look at the trapezoidal estimate. So we're missing, for the trapezoidal estimate, we're starting at 0, so we still need to actually find 0 f of 0, so let's just add in f of 0 up here. That is equal to 8. So for the trapezoidal estimate, let's just put right endpoint. So for the trapezoidal, I'll go up here. So it's going to be a half times f of 0 plus 2 times f of 1 plus 2 times f of 2 plus 2 times f of 3 plus f of 4. So we always multiply the ones that aren't the first or the last by 2. And so now we have a half times f of 0 is 8. 8 plus 2 times f of 1, which was 15 on 2, plus 2 f of 2 is 6, so 2 times 6 is 12, plus f of 3, so 2 times 7 on 2, plus f of 4 was 0, so plus 0. So this is half of 8 plus 15 plus 12 plus 7, which is equal to, so what's a half of 12 is 35 plus 7 is 42, which equals 21 units squared. And this was for the trapezoidal. So therefore the difference, so if we have trapezoidal estimate minus the right endpoint estimate is equal to 21 minus 17, which is equal to 4 units squared. So in summary, we can use the trapezoidal estimate to find the area under a curve. And again, what this refers to is just the sum of the areas of each trapezium. And again, if we look at the area of a trapezium, it's a half times a plus b all times height, where the height is generally a width of 1. However, again, if it was a half or a quarter, this is what you would let your h be. Something that I do want to draw your attention to that we went through during this lesson was, for example, let's say you had your first trapezium, so you would have a half times then f of, I'm going to call this f of a, then plus 2 times f of a plus 1, plus 2 times f of a plus 2, and so forth, until you get to the last value. Let's call that f of b. So it's essentially the last value. Okay, so the last trapezium that you're going to be working with. So again, you have a half at the start, and then because the first trapezium, f of a by itself, 2 times everything in between that, and then finally b, let's call that our last trapezium, you have that alone. So you're not multiplying that one by 2. So that's something that you can use as sort of a more generalized rule. Or if you're not comfortable with that, you can just simply find the area of each trapezium and add them together. Comparing estimates to exact areas, at times we may be asked to find the percentage error or difference. And again, to find this, we just find the estimated area minus the exact area, or the difference between the two. Again, you want to have this difference to be positive, all divided by the exact area, and then multiply it by 100% to find it as a percentage. In our next lesson, we're going to be looking at the fundamental theorem of calculus. So in this lesson, we're looking at the fundamental theorem of calculus. In particular, we're looking at this theorem, the definite integrals from graphs, and evaluating definite integrals with unknown functions. So the fundamental theorem of calculus, it states that the area under the curve, y equals f of x, for all x is an element of a to b, can be given by f of b minus f of a, where capital F of x is an antiderivative of lowercase f of x. So essentially, permitting x is continuous over the domain a to b, then we can write the integral from a to b of lowercase f of x dx is equal to capital F of b minus f of, or capital F of a. So again, basically, you first integrate, then substitute in the upper bound, subtract the lower bound. So it can also be referred to as the definite integral. So in previous lessons, we found an indefinite integral with the constant of integration, or we may have used the point to find the original equation. However, in this case, the definite integral refers, or it differs, as it calculates the exact area under a curve. So before we were provided with the exact area, whereas in this case, we can now find this exact area ourselves by setting up and evaluating a definite integral. This will generally be found over a certain domain, if it's provided, or between boundaries, so generally where the graph cuts the x-axis. So for example, if we look at the graph of f of x equals x squared plus 9, we can see this is above, or this is positive, it's sort of the region bound by the curve f of x and the x-axis would be between 0 and 3. So for example, to evaluate that definite integral, this could be written as something like 0 to 3, so the lower bound of 0, upper bound of 3 of f of x dx. And then we could go about evaluating this particular integral. Looking at some of the properties and language of definite integrals, so you have a is our lower bound, b is your upper bound, so lower bound and upper. Then if you have a scalar multiple, it treats it exactly like our integral properties. You can essentially take it out the front and it's going to multiply whatever the value that you get for your definite integral. If something starts and ends at the same value, so if our lower and upper bounds are the same, then the integral will just be to 0, because the area between the area under the curve, when they're the same, is going to be equal to 0. And this is essentially true because if you think about it, this is going to become f of a minus f of a is equal to 0, because essentially we're substituting in from that, and they will just cancel each other out. If you think about it graphically, let's say we had this really wonky looking curve. Let's change that up a little bit. If this is x equals a, underneath that same point, it's just going to be 0, because essentially there's nothing there. You have to have a second point that isn't the same. And again, we can show algebraically through substitution that it equals 0. Finally, again, using integral properties between a and b, for f of x plus or minus g of x, dx is the same. It would be the same as if you were to evaluate f of x and g of x separately. So you don't have to integrate both. If you like to separate it, you can, for as long as you then evaluate the integral of f of x and you evaluate the integral of g of x. So we have negative the integral of a to b of f of x dx. This is the same as the integral from b to a of f of x dx. So generally now we can see that our lower and upper bounds have changed. We're going to look at this in more detail when we get to finding the area underneath the axis. So when you sort of get negative areas, this property will come in handy. Finally, if we have the integral of integral of f of x from a to b dx, it can also be written from a to c of f of x dx plus c to b of f of x dx, only if c is between a and b. So for example, if you were to think about this graphically, what this would look like is we have a function, let's say some function like so. This is at a and this is at b. This is the same as if we had another value of c. So we can add essentially area 1 plus area of 2. So if you wanted to break that up, you could. They're the exact same, for as long as c is between a and b. So it's greater than a, but less than b. So you get some properties of definite integrals. So at the integral of negative x squared plus 3x dx between 1 and 4. So the first thing you want to do is take the integral of negative x squared plus 3x. So this will become negative x cubed on 3 plus 3x squared on 2. Now we don't have to put plus c because we're going to be substituting in. So I'm just write that as 4 and 1. Now we're going to substitute our upper bound first. This becomes negative 4 cubed on 3 plus 3 times 4 squared on 2 minus negative 1 cubed on 3 plus 3 times 1 squared on 2. So negative 4 cubed is negative 64 on 3 plus 48 on 2 minus then negative 1 cubed on 3 becomes still negative 1 on 3 plus 3 on 2. So now negative 64 on 3, I'll leave that as it is for the time being. 48 on 2 becomes 24, so plus 24. And then minus, so negative a third plus 3 on 2. I need the same denominator, so multiply the left-hand fraction by 2. So negative 2 on 6 plus the right-hand fraction, multiply that by 3, so it becomes 9 on 6. So we're left with negative 64 on 3 plus 72 on 3. Then minus 7 on 6 up here for the time being. Negative 64 plus 72, 72 is going to give us positive 8. So we've got 8 on 3 minus 7 on 6. Multiply the left fraction by 2. So again, you always need to have the same denominator. So this question is very fraction heavy. So it's going to become 16 on 6. Oh, sorry, that should be 7 on 6, not 7 on 2. 16 on 6 and minus 7 on 6. 16 minus 7 is 9. So we left 9 on 6. Can't leave your final solution like that. You have to simplify. So 9 on 6 simplifies to 3 on 2 units squared. So the first thing is integrate. substituting your upper bound, substituting your lower bound. You're going to subtract your lower bound from your upper bound, and then finally simplify until you get a final solution. Now let's have a look at the integral of 4 cos 2x plus 2 dx over the interval of 0 to pi on 3. So first thing we want to do is integrate 4 cos 2x. So this is going to become 4 times a half of sine of 2x plus 2x between 0 and pi on 3. So this is going to become 4 times a half is 2. So 2 sine 2x plus 2x pi on 3 and 0. So first thing you want to do is substitute in pi on 3. So 2 sine of 2 pi on 3 plus 2 pi on 3, then minus 2 sine of 0 plus 0. Sine of 0 is 0, and obviously 0 is 0, so therefore we're just left with 2 sine of 2 pi on 3 plus 2 pi on 3. So sine of 2 pi on 3 is root 3 on 2, so this becomes 2 times root 3 on 2 plus 2 pi on 3. So again, it's really important that you know all of the exact values from your circular functions. So the 2's will cancel out because 2 root 3 on 2 just becomes now root 3 plus 2 pi on 3 units squared. So again, you could write that all over the same denominator if you wished, but you don't have to in this particular case. So definite integrals from graphs. So when we are given a graph, we can identify boundaries. So we want to find the area under the curve. So we can also note this to be the area between the curve and the x-axis. So thus, to identify boundaries from a graph, we are required to find the x-axis intercepts. So for example, if we look at the graph of f of x equals 4 sine of x between 0 to pi, we can see that our x-axis intercepts would be the origin, so 0, 0, and obviously pi, comma, 0. So if we're to write this as a definite integral, then the area bound by this part of your sine curve would be given by the integral of 0 to pi of 4 sine of x dx. So again, it's always your lower boundary, your furthest left, and then to your furthest right, so 0 to pi. Show that 3x minus 6 on x plus 2 is equal to 3 minus 12 on x plus 2, and hence calculate the area of the region enclosed by this curve and the x-axis between x equals 3 and x equals 6. The first part of this question is to show that 3x minus 6 on x plus 2 is equal to 3 minus 12 on x plus 2. How do we go about doing this? First, I want you to think about, okay, well, the right-hand equation, we have a hyperbola. So this question here is essentially just a way of rewriting a hyperbola into asymptotic form. To do this, we can use long division, or you can just think about, how do I get from x plus 2 to 3x minus 6? I'm going to show you how to do it using long division, even though it really doesn't take that long in this case. So we're going to have x plus 2 and 3x minus 6. So now we can do 3x divided by x, so we're left with 3. Then we subtract. So 3 times x plus 2 is 3x plus 6. So now you will notice, well, 3x minus 3x is 0. Negative 6 minus 6 is negative 12. So therefore you're left with 3 minus 12 on x plus 2. Because negative 12 is our remainder, that's always going to be essentially divided by the divisor, what we're dividing by, so x plus 2. And you have 3 is by itself, and the 12 again was negative. So therefore we have 3 minus 12 on x plus 2. So we can use this form to now integrate. So to set up our integral, we want to find the integral between 3 and 6 of 3 minus 12 on x plus 2 dx. I'm going to separate this just to make life a little bit easier for ourselves. So it's going to be the same as 6 and 3 of 3 dx minus 12 times the integral of 3 to 6 of 1 on x plus 2 dx. So the integral of 3 is just going to be 3x. So it's 3x between 6 and 3. Then minus 12 times log e of x plus 2 between 6 and 3. So now we're going to substitute in our upper boundary and lower boundary for each of these sections. So it's going to be 3 times 6 minus 3 times 3, then minus 12 times log e of 6 plus 2, which is 8, minus log e of 3 plus 2, which is 5. And so therefore 3 times 6 is 18, minus 3 times 3 is 9. So 18 minus 9 is 9. So 9 minus 12 times log e of 8 over 5. The reason why we can write that as log e of 8 on 5 again is because you have the same base. Subtracting logs is the same as dividing what's inside. So 8 on 5, it can't be simplified any further. So we could leave that as 9 minus 12 log e of 8 on 5 units squared. So at times, especially in exams, we may not be given a function to integrate and then evaluate. Instead, we may be given the value of a definite integral and use this in our solution. So we actually don't know what the function is. We just know what it equals over a certain domain for some function, f of x or g of x, or whatever it might be. So if we look at this example, so given that the integral between 0 and 5 of f of x dx is equal to 8, and the integral between 0 to 5 of g of x is equal to 2, calculate the integral of between 0 and 5 of 2 times f of x plus 3 times g of x. So in this case, we have no clue as to what f of x and g of x may look like or how it may behave. However, we know it's going to be continuous over this domain of 0 to 5, and we know what the integral is over this period for each of these functions. So we have to sort of start to use our properties as to find the actual solution to this problem. So the first thing I'm going to do is rewrite this. So this is going to become the integral of 5, so it's 0 to 5, so 2 times f of x dx plus 3 of the integral of 0 to 5 of g of x dx. What you may notice now is actually, well, we have f of x by itself. We can notice this from before. So the integral between 0 to 5 of f of x dx is equal to 8. Well, hang on, I have this over here. So therefore, what you can do is substitute in 8 to wherever you see the integral of 0 to 5 of f of x. So this will become 2 times 8 plus, let's have a look at g of x. Again, you'll notice we're given that information. We're given g of x between 0 to 5, which in this case is 2. So therefore, this is going to be plus 3 times 2. So now our final solution is 16 plus 6, which equals 22 units squared. So we can use our properties to essentially manipulate it such that we can just recognize the information they've given us. And it's like, hang on, we actually have this integral. We know what this evaluates to. Now we can substitute it in and find what the question is actually asking for us. The area under the graph of y equals f of x between x equals 1 and x equals 4, where f of x is greater than a half over this interval, is 8 units. The area under the graph of 2 times f of x minus 1 over the same interval is, so I hope that you got the answer B, 13 units squared. So to get to this solution, let's have a look at the information that they've given us. So they've essentially told us between x is 1 and x equals 4, then the integral is equal to 8 units. So this means that the integral between 1 and 4 of f of x dx is equal to 8 units squared. So we know that it's equal to 8. They want us to find the integral of between 1 and 4 over the same interval of 2 f of x minus 1 d of x. This is what we want to calculate now based on this information. So again, let's split this integral. So we're going to have the integral of 2 times 1 to 4 of f of x dx, then minus the integral from 1 to 4 of 1 d of x. You can recognize now that we have been given the information for the integral of f of x between 1 to 4. That's 8. So this is going to become 2 times 8. Then minus, we can integrate 1. That's just going to give us x. So it's minus x between 1 and 4. So it's 16 minus 4 minus 1. So it's going to become 16 minus 3, which is equal to 13 units squared. So again, they've given you some information. You want to manipulate this information in order to substitute in the 8. And then, well, we can take the integral of 1. We know that's going to be x. Evaluate that integral so it becomes 3. And then have 16 minus 3, which is equal to 13 units squared. So whenever you sort of have these questions, you want to identify what the question's asking and what they've provided. So in this case, they've provided the integral of 1 to 4 of f of x. And then you can see they want us to find the integral of 2 times f of x minus 1 over the same interval. Manipulate, so you get 2 times the integral that they've given us, minus the integral of 1, and then evaluate. And finally arrive at your solution of 13 units squared. So to summarize, the fundamental theorem of calculus, essentially you want to first integrate, then substitute in your upper boundary, subtracting the lower boundary. You need to remember and apply your properties of definite integrals, so that whenever you have the same boundary, so a to a of f of x dx is going to be equal to 0. Remember the negative a to b of f of x dx is the same as swapping the boundaries from b to a and becoming positive. Scale factor and addition and subtraction, and finally where you have your third variable, for example, when you have that middle value of c. Calculating integrals with unknown functions, you obviously want to identify the value of the integral from the information provided, so see what they've given you, transpose the integral that you're asked to solve, and then substitute the provided information into your transposed interval and evaluate. In our next session, we're going to be looking at the area under a curve. So you may be wondering why there's a bouzouki on this screen. So a bouzouki is just a Greek musical instrument similar to that of a guitar. The reason why it's there is because essentially whenever we're looking at applications of integration, we can also use this to find the surface area. So for example, we could use integration to find the surface area of the flat surface of this bouzouki. In this lesson, we're looking at area under a curve. In particular, we'll be looking at signed area, total area, area between f of x and the x and y axis, as well as using definite integrals to solve for unknowns. Let's begin with signed area. So areas above and below the x-axis. Firstly, for regions that are above the x-axis, that is f of x is greater than 0, the signed area is positive. For regions that are below the x-axis, that is where f of x is less than 0, the signed area is negative. So let's consider the function y equals sine x, where x is an element of 0 to 2 pi. So we'll notice that we have a1 and a2, so 2 areas. The other thing that we can notice about a sine graph is that it is symmetrical. So the area a1 has to be equal to the area a2. However, the difference here is because a1, this part of the graph, is where f of x is greater than 0, and a2 is where f of x is less than 0. So therefore, even though the areas are the same, if we were to add them together, technically speaking, a1 plus a2 would equal 0 if we're considering the signed area. So a tip that I have is the definite integral calculates the net signed area and not the total area. So you have to be careful when interpreting the question. If it is asking for the signed or total area, in many applications they are more likely to ask for the total area. So for example, in this instance, we have a1 is positive, a2 would be negative. However, because we know that they are equal because the sine graph is symmetrical, we could simply multiply a1 by 2 to get the total area. But first we'll look at more applications and more examples of signed area. So calculate the signed area for the function f of x equals x squared minus 4 over the interval negative 4 to 4. So the first thing we're going to do is sketch this graph. So f of x equals x squared minus 4, we know this is a parabola that's being translated down by 4 units. We also have x-intercepts and endpoints. So the x-intercept, we let y equals 0, so we can evaluate. So we're going to have 0 equals x squared minus 4, therefore x squared equals 4, x equals plus or minus 2. So let's say they're roughly here. So negative 2, 0, 2, 0. And we also have endpoints. So where x is negative 4 and 4, so we have to also calculate these. So where x equals negative 4, we can substitute in. So f of -4 equals -4 all squared minus 4, which is going to give us 16 minus 4, which equals 12. So therefore 12, let's say it's probably going to be up here somewhere. -4, 12. And again, because the parabola is symmetrical, we can probably know that if we're substituting x equals 4, we'll get the same result. So f of 4 is also equal to 12. So therefore, let's put that point in for 12. And now we can sketch our parabola. Okay, so it's going through those points. So calculate the signed area. So what we can see is, I'm going to call this A1, that's above the axis. And A2 here is below the axis. So because it's symmetrical, all I can do is multiply A1 by 2 and then multiply A2 also by 2. To calculate this net signed area, what we can do is simply take the integral. So signed area will equal 2 times the integral from -4 to 0 of x squared minus 4 dx. So now we can evaluate this integral. So it's going to be 2 times x cubed on 3 minus 4x between -4 and 0. Substitute both of these values in. So we're going to have 2 times 0, because 0 cubed on 3 minus 4 times 0 is just 0. Then minus, now we're going to substitute -4. So -4 cubed on 3 minus 4 times -4. So this becomes 2 times -4 cubed is -64. So -64 on 3, or minus all of that. Then plus 16. I'm just going to come up here. Then now we have 2 times, so 0 minus that is going to become 0 minus -64 on 3. We can't simplify that. However, we can, whenever we add fractions, we want the same denominator. So multiply 16 by 3. So we're going to have 48. So -64 plus 48 gives us -16 on 3. So therefore we have 2 times negative becomes a positive. So 2 times 16 on 3 will equal 32 on 3 units squared. And that is the net signed area for f of x over the interval of -4 to 4. Calculating total area. So to calculate the total area between a curve and the x-axis, we must ensure that any region below the x-axis is now positive. To do this, we can use the integral property, negative integral of a to b of f of x dx, or we can flip the bounds is equal to a or b to a of f of x dx. So either one of those two will work for whenever we want to make a negative area positive. So let us consider the function now y equals sine x, where x is an element of 0 to 2 pi. So same thing, we've looked at this example previously. So if you were to find the total area, so we can see that a1 is equal to the integral of 0 to pi of sine of x dx. And a2, because it is below the axis, we want to either flip the sign, so you can write that as 2 pi to pi of sine of x dx, or it equals negative the integral of pi to 2 pi of sine of x dx. Either way that you write that integral is correct, because it will make that negative solution now positive. And that way then you can now add them together to get a positive solution for the total area of a1 plus a2 rather than the net signed area. So you could say, therefore, total area equals the integral of 0 to pi sine of x dx minus the integral of pi to 2 pi of sine of x dx. Or you could again flip the bounds. It's your choice. One of those two will result in the same solution. So area between f of x and the axis. To calculate the area between a curve and the x-axis, we have to either be provided with certain values for x, or we have to find the x-axis intercept. So let us consider the function y equals -x squared plus 4, where x is greater than 0. So in this case, we've got a parabola and it's been reflected. So therefore we know we're going to have a maximum turning point at y equals 4. So it's going to become 0, 4. And x is greater than 0, so therefore it's going to be something like so. So if we're looking for the area between f of x and the x-axis, we're looking for this area here. In order to find this particular area, we need to know what the x-axis intercept is. So that's the first thing we're going to do. So x-axis intercept, we let y equals 0, so 0 equals negative x squared plus 4. We subtract 4, so negative 4 equals negative x squared. Therefore, x squared equals 4. And finally, x equals plus or minus 2. And because x is greater than 0, we know this solution will be 2, 0. So how do we find this area? We can now set up our definite integral. So we're going to have the integral from 0 to 2 of negative x squared plus 4 dx. If we want, we can evaluate it. So why not? Let's take the integral. So we're going to have negative x cubed on 3 plus 4x between 0 and 2. Substitute in, we're going to have negative 2 cubed on 3 plus 4 times 2. And you'll notice minus 0 is 0, so therefore we're left with negative 8 on 3 plus 8. We need the same denominator, so multiply 8 by 3, we get 24. So we're left with negative 8 on 3 plus 24 on 3. And therefore the solution is 16 on 3 units squared. So the first step for this particular problem, find your x-axis intercept if you're not given a certain x value, and then set up your definite integral and evaluate as we've done in the past. So area between f of x and the y-axis. So to calculate the area between a curve and the y-axis, there are two methods that we can use. First, we can transpose the function and then integrate with respect to y. That's the important part. You have to integrate with respect to y rather than x. Or you could subtract the area under the curve from a rectangle. So we'll go through both methods. In this example, we'll use the first method, integrating with respect to y. So let us consider the function y equals the square root of x plus 4, where x is an element of 0 to 4. First, before we transpose, what I want us to recognize is we've got a square root graph that's been shifted up by 4 units between 0 to 4. So that's the first thing I'm going to do is draw this graph. So we're going to have 0, 4. And now we sketch this between 0 to 4. So let's find this endpoint. So it's going to be the y equals the square root of 4 plus 4 equals 6. So this point here is 4, 6. And we want to find the area between this curve and the y-axis. So in this case, the shaded one that I've just done. So if we transpose with respect to y, so we're going to have y minus 4 equals root x. So essentially we're solving for x because we will integrate with respect to y. We're going to have y minus 4 all squared is equal to x. However, you'll notice that we have the negative arm of a parabola. So for example, y minus 4 squared would look like so. We've got the positive arm where y goes between 4 to 6. So therefore, in this case, y is going to be greater than 4. Or if we want, we can write this as 6, not 6. We'll write it the other way around. It's going to be 4 is less than or equal to y, which is less than or equal to 6. So it's our current sort of domain for y, if you like. So setting up our definite integral, we'll have from 4 to 6 of y minus 4 all squared dy. And this is going to be equal to 8 on 3 units squared. And I've just put this into the CAS. You could also do this by hand. You could expand out or use the particular property. But in this case, I've just done it on the CAS to get us 8 on 3 units squared. So again, when finding the integral in terms of y, you'll also be required to find the terminals also in terms of y. So this can be done by using the y values from the original x values that you provided. In this instance, we'll provide it with the x values from 0 to 4. So I found those endpoints, and then I referred to the y values as our bounds for the integral. So in this case, from 4 to 6. Using definite integrals to solve for unknowns. So this occurs when we are given the value of an integral and one of the terminals. So that means we have to use this information to solve for the remaining terminals. So for example, to solve these problems, we can use the following steps. So we can integrate f of x, we can substitute in the given terminals. One of these may be a pronumeral. So for example, let's say the integral of sine x between 0 and m equals 2. We would evaluate that integral with respect to m, and then we'd have to eventually solve for m, solve for the unknown pronumeral. The integral from 1 to k of 2 on x dx equals log e of 4. Determine the value of k. So the first thing I want to do here is integrate our 2 on x. So this is going to become 2 times the integral of from 1 to k of 1 on x dx is equal to log e of 4. So let's keep that in mind. So now the integral of 1 on x was just log e of x. So it's going to become 2 times log e of x between k and 1 is equal to log e of 4. So therefore 2 times log e of k minus log e of 1 equals log e of 4. You'll notice log e of 1 becomes 0, so using those log laws, log base anything of 1 will always, in this case, equals 0. So log e of 1 is 0. So this will become 2 times log e of k is equal to log e of 4. So therefore log e of k, this becomes log e of k squared equals log e of 4. And therefore you have k squared is equal to 4. Therefore, k is equal to plus or minus 2. And because k would, in this instance, have to be greater than 1, because 2 on x is technically, it's a hyperbola, so therefore there's an asymptote at 0, so it has to be greater than 1. So as k has to be greater than 1 in this particular instance, therefore k is equal to 2. And again, just to reiterate that message, you have a hyperbola, so it's going to look something like so. If you've got x equals 1 at this point, and then you've got k at this point, that's the area you want to find. You can't find the area over an asymptote. So therefore, you had to recognize that k has to be greater than 1 because it's 1 to k, and then recognize to choose k is equal to positive 2 rather than negative 2. You can't go backwards over an asymptote. So let f be defined for all real numbers except a half, where f of x equals negative 6 on 2x plus 1 plus 3. The area bound by the curve and the y-axis over the interval x is an element of 3 on 2 to 7 on 2 is closest to. So I hope that you got the answer 0.58 units squared. And we'll take a really close look at this particular problem because we are looking for the area bound by the curve and the y-axis. So again, the first thing we want to look at is our endpoints. That's the first thing I want to calculate. Again, we'll notice this is a hyperbola that's being reflected, but let's look at our endpoints first and foremost. So f of 3 on 2 is going to be equal to negative 6 over 4 plus 3. So that's equal to negative 3 on 2 plus 3, which is equal just to 3 on 2. So that's one of the endpoints. So we've got 3 on 2 and 3 over 2. And then now if we look at f of 7 over 2, this is going to equal to negative 6 over 8 plus 3, which becomes negative 3/4 plus 12 on 4, which is equal to 9 on 4. So having found our endpoints, now let's look at what this graph may look like. So it's been shifted up by 3 units, and we know there's going to be a horizontal asymptote at this point, and it's been reflected, so therefore we will have something looking like so. So let's put that in, probably steeper, but nonetheless, let's not worry about the scale for the time being. So this is going to be 3 on 2, 3 on 2, and then we've got 7 on 2 and 9 over 4. So what we want to find is the area between this curve and the y-axis. So what we can see now is we want to find this shaded region. So because it's over the interval x equals 3 on 2 and x equals 7 on 2, so we want to find this shaded region. And to do that, we can find the area of the total rectangle and subtract the area underneath the curve. So essentially the area of the shaded region will just equal 9 over 4 times 2. So that's the area of the rectangle, because the distance between these 2 points is 2 units, because 7 on 2 minus 3 on 2 is equal to 2. And we're going to subtract the integral of f of x between the points 3 on 2, 7 over 2 of f of x dx. So that will give you the total area between the curve and the y-axis. And then so now we can put this into our CAS. So again, we have 9 on 4 times 2. Put that in brackets, and we're going to subtract the integral. So menu for 3 of from 3 on 2 to 7 on 2 of negative 6 on 2x plus 1 plus 3 dx plus 3, then dx, or not dq. Let's try that again. So dx, where's my x? There it is. We now press enter. Again, you'll notice you'll get an answer in, potentially you'll get an answer in exact values. So just press Control Enter to get that in that form. 0.579, so that rounds to 0.58 units squared, and again, the answer is C. So in this case, again, we've got the solution of C, so 0.58 units squared, and we actually used the second method where we found a rectangle, so we're using the height of 9 quarters because it's the height of our rectangle in this case, and then the width being 2, so or the length, 2 times the height, so 2 times 9 on 4, and then we just subtracted the area underneath the curve, so in this case the area, the blank area of that rectangle, and found the answer to be 0.58 units squared. So either way, either of the two methods you can use in order to find the area between the curve and the y-axis. So in summary, there is a lot to get through in this lesson. So we looked at signed and total area. So the key thing to remember about signed and total area is that anything below the axis will give you a negative value for the area. So if you do calculate the integral, this will give you the net signed area. If you want to find the total integral, you do have to change either the bounds or make it negative, referring to those properties below. Solving for unknowns with definite integrals. So again, to solve these problems, we can use the following steps. We can integrate. We can then substitute in the given terminals. One of these, again, will be a pronumeral. Let the integral equal the value provided, and then finally solve for that unknown pronumeral. The area between the f of x and the x and y axes. So f of x and the x-axis, we can simply find our bounds that may either be provided, or we may have to find the x-axis intercept. And for the y-axis, we'll have to first transpose and integrate with respect to y, or we can subtract the area under the curve from a given rectangle, similar to what we did in the mega question activity. In the next lesson, we look at other applications of area under a curve. So again, you'll see that we have a bouzouki on our slide, and last time I spoke about how we could find the area of the flat surface. And in this case, again, we can still do the same. We can find that area. However, we could find two functions that relate to each side of the bouzouki. So in this case, if you were to sketch this on a graph, for example, you could have something looking, and then you could have something going like that as well. And we could find, maybe let's make them connect. So we could find that point of intersection and then find the areas between those two curves. That's what we're going to be looking at in this lesson, finding the area between two curves. So in this lesson, we're going to be focusing on area under a curve, part 2. In particular, we're going to be looking at area between functions and area between f of x and the inverse function. So area between functions, the region bounded by two or more functions with no intersection. Case 1 is where the region is where f of x is greater than 0 and g of x is greater than 0. So let f of x and g of x be two continuous functions where f of x is greater than g of x. So again, all we'll have to, in this instance, look at is we're going to have the integral. We're looking for the area between these two functions. Case 2 is where the region is where f of x is less than 0 and g of x is less than 0. So again, let f of x and g of x be two continuous functions. In this case, f of x is less than g of x because it's essentially more negative than g of x is less than the axis. Case 3 is where the region is where f of x and g of x pass the x-axis. So let f of x and g of x again be two continuous functions, where now f of x is greater than g of x. Something that I really want to touch on, particularly in this case, and I'll get to the formula in a moment, is that whenever we have this third scenario where both graphs potentially may cut the x-axis and become negative, we don't have to worry about taking this into account now, because if we were to shift both of these functions up by the same value, then they would be in the positive x-axis. So for example, we could essentially shift this graph by x units, or let's say k units, just to not get confused. So let's say, as an example, 3 units. For as long as we shifted both of these functions up by 3 units, the area between them will still be the same. So therefore, we don't have to worry about taking into account the negative area in this case, because we've got two separate functions. This is different when we're working with just one singular function and finding the area under a curve. Because we're finding the area between two curves, we don't necessarily need to take this into account now, because we could technically move both of these functions up by a factor of k. So the area between two functions in each of the three cases is essentially going to be the integral from a to b of f of x minus g of x dx. So again, f of x is your top function, the function that is on top, subtracting g of x, the function that is on the bottom. Let f of x equal 2 times x minus 2 all squared plus 2, and g of x equals x minus 2 squared plus 1. What we'll notice here is the black line is f of x, and the green line is g of x. And we can see this because of our turning point. So the turning point of f of x is at 2, 2, and the turning point of g of x is at 2, 1. So that's just how I've identified those two functions. We'll notice that f of x is greater than g of x in this instance, and we want to now find the exact area of the region between over the interval 0 to 4. So we want to find this sort of shaded region in here. So we don't necessarily need to find the y values of the endpoints. All we need is the x. So we've got 0 to 4. So now we can set this up. So 0 to 4 of f of x, which is 2 times x minus 2 all squared plus 2 minus x minus 2 all squared plus 1 dx. I'm just going to expand and simplify. So we have the integral of 0 to 4 of 2 times x squared minus 4x plus 4 plus 2 minus x squared minus 4x plus 4 minus 1 dx. And then now we would have the integral of 0 to 4 of x squared minus 4x plus 4. The minus 2 minus 1 is going to be 1, so plus 1 dx. We're left with 0 to 4 of x squared minus 4x plus 5 dx. What happened before? So because we had 2 times x squared minus 4x plus 4, and we're subtracting just x squared minus 4x plus 4, essentially, if you had 2 times x minus 2 squared, we can just take away one of them. So it just becomes, essentially, you'll just be left with x minus 2 all squared, because we had 2 of them. Subtracting 1, we're just left with 1. So 1 perfect square of x minus 2 squared, then expands out to x squared minus 4x plus 4, and then again minus 1 plus 2 minus 1 gives us plus 1. Now we can integrate, so we're left with x cubed on 3 minus 4x squared on 2, which will just become 2x squared plus 5x between 0 and 4. I'm not going to worry about the 0 because it's just all going to become 0, so let's substitute in the 4. So we have 4 cubed on 3 minus 2 times 4 squared plus 5 times 4. 4 cubed is 64 on 3 minus 2 times 16 is 32 plus 20. We're left with 64 on 3 minus 36 on 3. The 36 comes from negative 32 plus 20 is negative 12. Negative 12 times 3 to get the same denominator gives us negative 36. And therefore your final solution is going to be 28 on 3 units squared. So again, you can always expand out, then collect your like terms, and then integrate. That works the same as well. So looking at the area between functions, so the region bounded by two or more functions with intersections. So in this case, this is one region bound by two curves. So to calculate the area bound by two curves that intersect, we have to identify their boundaries or terminals. So in the previous example, in the previous multiple choice activity, we were given a boundary, we were given -1 to 1. In this case, we have to find them, and generally, to find these terminals, we have to find the points of intersection. So in this case, to set up this particular problem, we have to find these 2 points of intersection. You could do it algebraically in this case because we can see it quite clearly graphically. We can see the point is at 2, 4 and at -2, 4. So again, when we're setting our terminals, we're only worried about the x-axis value or the x values. So therefore, the integral will be the function that's on top, which is g of x. So between -2 to 2 of g of x minus f of x dx. So that's how you go about setting up your integral. You could also do it, in this case, because parabolas are symmetrical, you could write this as 2 times the integral from 0 to 2 of g of x minus f of x dx. That will work as well, because again, what we can see is this area is going to be equal to the one that's been reflected on the other side of the y-axis. So therefore, you can write them either way. You get the same solution. The region, again, bounded by two or more functions with intersections. So we've got multiple regions bound by two curves is our second case. So when calculating these areas, we can use the steps below. So we want to find the points of intersection, similar to before, identify which function is on top, set up and calculate the definite integral as our final step. So for functions with multiple areas, we use this process and then simply sum the areas of each region. So for example, in this case, we've got f of x equals sine x and g of x equals sine 2x. If we were to find the area bound by these two curves, so this is A1, and then I'm going to call this large area A2. So the total area is equal to A1 plus A2. So obviously in this case, I'm not going to worry too much about the points of intersection. I'm just going to call this one obviously is the origin, so 0, 0. I'm going to call this, let's call it a comma f of a, and let's call that point, we know that's pi comma 0. So to set this up, for example, we can see in area 1 that g of x is on top, so area 1 will equal the integral from 0 to a. We don't know what a is, I'm just using that hypothetically speaking to help us set up our integrals. We're going to have g of x is on top, so g of x then minus f of x dx, and then we're going to plus the area between both, so it's going to be f of x is now on top, so between a to pi, so we're going to have f of x to an x minus g of x dx, and that will give us our total area. Again, even though this area here, A2, is technically, there's a part that's bound by the, that goes below the x-axis. Again, if we shifted both of these graphs up, we would still get the same solution. So therefore, we don't have to worry in this case when we're working with two curves. So let g be defined between 0 and 4 pi on 3, where g of x equals sine of x and f of x is equal to root 3 cos of x. Calculate the area of the larger region bound by the curves f of x and g of x. So in this case, I want to first sketch these graphs roughly to see what it may look like. So we're going to have sine of x between 4 pi on 3. So it's going to, I'm just going to get it a 0 to 2 pi sketch for both of these, root 3. So therefore that's a 1. Root 3 is going to be just greater than 1. So it's going to be cos. So it's going to probably be up here. So between 0 and 4 pi on 3, so we're going to find the endpoints in this case, but let's just have a look at where the points of intersection are because we're looking to calculate the larger region. In this case, the larger region will be this shaded region here, so we have to find the 2 points, or those 2 points of intersection. So the first thing I want to do is let them equal each other to find the points of intersection. So we can have sine of x is equal to root 3 cos of x. You'll notice if we divide by cos, we'll get tan. So we'll divide both sides by cos. So we get tan of x is equal to root 3. And at the moment, x is an element of 0 to 2 pi. Even though we do have it is defined between 0 and 4 pi on 3, but let's just use this to find our points of intersection for the time being. So but then we're going to be left with, when is tan positive? Tan is positive in the first and third quadrants, so Q1 and Q3, and tan of root 3. The symmetry property for Q1 is just theta. Q3, the symmetry property is pi plus theta, so therefore if theta equals, so it's 60 degrees, so it's pi on 3. Therefore we're going to have pi plus pi on 3. So therefore the point of intersection is equal to pi on 3 and 4 pi on 3. So that's actually our endpoint at 4 pi on 3. So it's going to be, that's 4 pi on, x is equal to 4 pi on 3. And here x will equal to pi on 3. Doesn't matter too much about our y, the y value of the point of intersection, because we need the x values to set up our terminals. So now we can have the integral of, what we'll notice on top is the sine function. So we're going to have from pi on 3 to 4 pi on 3 of sine of x minus root 3 cos of x dx. So now putting this together, so the integral of sine of x is negative cos of x. So we're going to have negative cos of x, then minus the integral of cos is sine. So therefore it's minus root 3 sine of x between pi on 3 and 4 pi on 3. Now substitute these values in. So we're going to have negative cos of 4 pi on 3 minus root 3 sine of 4 pi on 3 minus negative cos of pi on 3 minus root 3 sine of pi on 3. So this will become, so cos of 4 pi on 3 is going to be negative a half. So negative a half becomes a half. So a half. Then minus root 3 sine of 4 pi on 3 is going to be negative root 3 on 2, because sine of pi on 3 is root 3 on 2, but 4 pi on 3 is in the third quadrant. Sine is negative in the third quadrant, so it's going to be times negative root 3 on 2, then minus negative cos of pi on 3, so it's going to be negative a half, then minus root 3 sine of pi on 3 is root 3 on 2, so times root 3 on 2. So now we're going to be left with a half minus root 3 times negative root 3, so it's actually going to be plus, is just going to be 3 on 2, and then minus negative a half minus 3 on 2 is going to be negative 4 on 2, so negative a half minus 3 on 2, so we're left with a half plus 3 halves are 2 wholes, so 2, then minus negative 2 is equal to 4 units squared. So the first thing here we wanted to do is equate our two functions, find the point of intersection. We found that to be pi on 3 and 4 pi on 3, and then use that to evaluate the definite integral, identify which one was on top. So in this case, sine of x was on top, f of x was on the bottom, root 3 cos x, and therefore then evaluate your definite integral. So there will be times where something like this pops up and you'll have cos, sine, and eventually tan that you have to deal with. So again, circular functions pop up in integration, so do any other functions, log, exponentials. It's really important that you're aware of all those laws and index rules, or anything, as well as your exact values in this case. Finding the area between a function and its inverse. So let's consider the following graph. We have f of x equals x squared on 2, and its inverse of x equals the square root of 2x. So what we can see here, to find the area between these two graphs, we're looking for this area here, and essentially again we can set this up the same way, identify which function is on top, and then identify where the functions intersect. So in this case, we could theoretically have the integral from a to b of f inverse of x minus f of x dx. That works. What we can also notice is you could find, so the area between a function and the inverse can be found by using the following formula that we've given, if and only if one of their points of intersection is at the origin. So this b squared minus 2 times a to b of f of x dx, what that means is essentially, if we look at this square, so this is going to be, so b is 2, so therefore 2 squared. We have that square, then we can subtract 2 times the area of that, and it will give you the black shaded region between the two curves. So that will always work if and only if you have the inverses intersect at the origin, but generally speaking, if you want to be safe, you can use the normal way to find the area between two curves, where you find the curve that is greater on top of the smaller curve, and then find their points of intersection. That works as well and will work in all cases, and even if they don't intersect at the origin. So it's probably a safe one, but it's a neat little trick that you could potentially use for some of these problems. So let f be defined for all real positive numbers where f of x equals log e of x plus 2. Calculate the area of the region bound by f of x and its inverse between their points of intersection. So in this case, what we can do whenever we first need to find the inverse function. And again, we can do this all in our CAS. To find the inverse function, we normally swap x and y. Menu algebra solve. So x equals log e of y plus 2. So let's go with log e of y plus 2. And we want to solve for y. Press enter. So therefore, our inverse function is going to be e to the negative x minus 2. So we want to find their points of intersection now. So again, we're going to use solve. So menu algebra solve log e of x plus 2 of x plus 2 is equal to the x minus 2 comma x. So if we have 2 points of intersection, x equals negative 1.841 and x equals 1.146. Because the answer we want is to 3dp, I'm going to use 3 decimal places here as well. So we're going to go with menu. Now integral, and log e of x log e of x plus 2 will be the top function, because e to the x minus 2 is being shifted down, so therefore we can know that log e of x plus 2 is on top. So if you were worried, you could check the graph of these functions to determine which one is on top. So in this case, we want to find we've got the two x-intercepts, the two x values of the points of intersection. So therefore it's negative 1. Let's go with 8414 and to 1.1462. I'll do that. 4 decimal places should be ample. And then we have log e of x plus 2, then minus e to the x minus 2, minus 2 dx. That's incorrect. So let's just copy that. The reason being is because I didn't put a bracket around the minus of e to the x minus 2, so it's assuming that we're still subtracting that 2. But let's put a bracket in between there because we're subtracting the whole function of e to the x minus 2. And therefore we're left with a solution of 3.898. We can write that in. So therefore, the integral from negative 1.8414 to 1.1462 of log e of x plus 2 minus e to the x minus 2 dx is equal to 3.898 units squared to 3 decimal places. So again, find your points of intersection, or in this case we had to first find the inverse, find the points of intersection, identify which is on top, and then calculate using our CAS in this particular scenario. So consider the graphs of the functions f and g shown below. The area of the shaded region could be represented by which of the following? So I hope that you selected D, and we'll take a little bit of a closer look at this as well. So if we notice, we're trying to find the area of the shaded region. And what we can see is that the dotted line here is y equals f of x. So f of x is our top function. and g of x is our lower function. However, we can see that f of x is essentially defined for 0 to d. So the area of f of x would be from 0 to d of f of x dx minus the integral from a to c of g of x dx, and that is the solution given by d. The others are there really just to confuse you. We can see the total area of f of x is defined between 0 to d, because that's the area between f and the x-axis, and we want to subtract the area from g and the x-axis, and that's only defined between a to c because they're the two x-intercepts of that particular function. So again, we want to find the total area of the shaded region, so therefore it's going to be your f of x goes from 0 to d, and you want to subtract g of x, which only goes from a to c. Really important that you don't have to necessarily have the same bounds all the time. It's just in this case, we're finding the area that sort of is shaded and goes between the functions and the x-axis. So in summary, when we're looking for the area between two curves, to calculate this, we can first identify their boundaries or terminals through solving the simultaneous equation, so equating both functions, finding their point of intersection, identify which function is greater, i.e. on top, and then using the x values as the terminals for the integral and evaluate. So next lesson, we are going to be looking at the average value of a function. So again, we see this bazooki at the start of our lesson, if you like, and you may be thinking, what now? What can we possibly look at this instrument in any more detail regarding integration? So actually, we can think about the sound that it makes. So for example, if we think of a sine graph or the sine curve, this could represent the sound coming from this bazooki. So for example, let's say we had a graph that looks something like so. We can actually use integration to find the average sound that the bazooki makes, or the average volume, if you like. So in this lesson, we'll be looking at the average value of a function. In particular, we'll be looking at the average value of a function and using the average value to find unknowns. So the average value of a function, firstly, we're going to look at the average value formula. So the average value of function f for an interval where x is between a and b can be defined as 1 divided by b minus a times the integral of f of x between a and b. So the average value represents the height of a rectangle that has the same area as the integral of f of x over this interval. So if we take the example here to our right, so f of x equals sine of x plus 1, essentially that average value will be equal to the rectangle, or the y value, the height of that rectangle, over this particular interval. So for example, we could calculate this average value by finding 1 divided by 2 pi minus 0 for the integral between 0 to 2 pi of sine x plus 1. So in this example, we'll find the average value of the function f, where f of x equals cos of x on 2 plus 2 over the interval of 0 to pi. So the first thing I want to bring our attention back to is the formula. So we know the average value is equal to 1 over b minus a times the integral from a to b of f of x dx. Now let's substitute the information that we have. So we know it's over the interval of 0 to pi, so it's going to be 1 over pi minus 0, the integral from 0 to pi of cos of x on 2 plus 2 dx. So then now this would become 1 on pi times 1 over 2, so it becomes 2 sine of x on 2 plus 2x, again between 0 and pi. Substitute this in, so we get 1 over pi times 2 sine of pi on 2 plus 2 pi, and then we're going to subtract the substitution of 0, so it's going to be 2 sine of 0 plus 2 times 0. 2 sine of 0 is just 0, so therefore we're left with 1 on pi, and 2 sine of pi on 2 is just 1, so 2 times 1 is 2. So we're left with 2 times 1 plus 2 pi, and so this will become 2 plus 2 pi over pi. So that would be our average value for this function f of x over the interval 0 to pi. So using the average value to find the unknown. So at times, particularly in the exam, you may be asked to find the unknown value once you're given the average value of a function already. So for example, you could use this information to solve for an unknown, which Generally, it would be one of the terminals. So for example, you could have something like, let's say the average value between 1 and 2 minus a, so therefore it's between a and 2 of f of x dx was equal to 4. So in this instance, what you would do, you could put that into your calculator and solve. If it's something that you could do by hand, let's take a look at some steps you could use to approach this kind of problem. So first, you would substitute the given information into the average formula, so you'd have something similar to what you can see on the screen. You would equate the equation to the given average value, so again, in this case, we've equated it to 4. You would then evaluate the integral in terms of the unknown, so again, you'd substitute in, you'd find it in terms of a, then eventually you would solve for that unknown, so you'd solve for a in this particular case. So for questions that you could do by hand, you would have to show what you're working out. However, there will be instances where you could use your CAS and you would have to use menu 3.1 using solve. Let's now take a look at an example. So the average value of the function f of x equals 2 sine of x minus pi on 6 over the interval pi on 3 to a is equal to 2. Find the value of a. So in this case, the first thing you want to do is set up your average value formula. So again, we can say we're going to have 1 over a minus pi on 3 times the integral from pi on 3 to a of f of x in this case is going to be 2 sine of x minus pi on 6 dx, and this has to be equal to 2 because that's what they've told us in the question. So now if we would like, we could put this in our CAS, so we could do this as solve. Then we have to do comma a because that's the polynomial that we're solving for. So now to evaluate this into our calculator, we would go with menu 3.1, so you want to solve, and then you type in 1 divided by a minus pi on 3, where is a? So a minus pi over 3, then times the integral, so menu 4.3, that's going to be from pi on 3 to a of 2 sine of x minus pi on 6 dx. And they told us that the average value equals 2, so we're going to put equals, or not in that part, let's make sure we get out of that, and then equals 2, then comma a, because that's what we're wanting to solve for. And press enter. So therefore a will equal 1.047. The graphs of functions f and g are shown below. Both functions have the same domain, 0 to b, where b is greater than 0, and the same average value. The value of b is, so I hope that you selected D, b equals 8. So what we can see from our triangle, so we know that the average value is again just essentially 1 over b times the area of our triangle. So in this case, we've got a triangle, it's half times base times height. So it's going to be 1 over b times a half times the base is b times the height is 2b. So this is going to be equal to 1 times b times 2b is 2b squared over 2b, which just equals b. And now if we take a look at our graph, the graph on the right hand side, the average value there would again be 1 over b times the area of that would be b times 8, because base is b, the height is 8, so this would just equal 8. Considering that they have the same average value, therefore b is equal to 8, because essentially the average value for f is equal to b, and the average value for g is equal to 8. Equating them, we get b equals 8, and therefore your solution is D. So in summary, the average value formula, you have 1 divided by b minus a, where b is obviously the upper bound, a is the lower bound, between a to b of f of x dx. When you want to find unknowns using the average value, you substitute the given information into the average value formula, you equate the equation to the given average value that they've provided, evaluate the integral in terms of the unknown, and then solve for the unknown. And again, if you're doing this on your CAS, make sure you put comma the polynomial that you're solving for instead of sometimes students do comma x. We're integrating with respect to x. We're trying to find the polynomial, in our case, has been a. So in our next session, we look at the application of integration to kinematics. So here you can see that someone's about to bungee jump or is in the process of bungee jumping. And you may think about what does integration have to do with bungee jump. In this lesson, we'll look at ways in which we can find the total distance traveled whilst bungee jumping, as well as the net difference in the starting position and finishing position of this person doing this bungee jump. So in this lesson, we'll be looking at application to kinematics. In particular, we'll be looking at the relationship between position, velocity, and time, the average velocity and average acceleration, and distance and displacement. So here we're going to start with the relationship between position, velocity, and acceleration. So if we look at, so let's say we start with the position, x of t, and we want to move to, so this is position, and then we want to find the velocity of something that's moving. We can then derive it. So velocity is equal to x dash of t, because we want to derive. And then if you want to find the acceleration, you derive again. A of t, which is equal to v dash of t, or which is equal to x dash dash of t. X dash dash of t just means the double derivative. So essentially you're deriving the position twice. So once you get to the velocity, you just derive that again. So again, we can see we derive. So to move from position to velocity to acceleration, you derive. Well, if you want to move from acceleration to velocity, so in the other direction, you integrate and you anti-derive. So essentially you can also write the velocity as the integral of the acceleration. And then integrating again, you get the position. So that means we could write that as the integral of the velocity. And again, this is summarized in these three formula boxes. A particle starting from rest accelerates according to the rule a equals 4t times 2 minus t. After 3 seconds, the velocity is equal to 4. Determine the equation that models the velocity of this particle. So we've been given the acceleration. So what we can recognize, we've got a of t, I'm just going to expand this out, is equal to 8t minus 4t squared. We've also been given a point. So we know that after 3 seconds, so when t equals 3, the velocity is equal to 4. So v equals 4. So therefore we could write that as a point. So v of 3 is equal to 4. So we'll come back to that in a moment. So now we want to find the velocity. If we think back to the previous line, velocity is equal to the integral of acceleration. So v of t is equal to the integral of a of t dt. So that's exactly what we want to do. We want to integrate this now. So we're going to have the integral of 8t minus 4t squared dt. So integrate, this will become 8t squared on 2 minus 4t cubed on 3 plus c. Simplify. So this will just become 4t squared minus 4t cubed on 3 plus c. So this is v of t. However, we know we have a point. So we have a point, we can now solve for c. So we're going to have 4 equals 4 times 3 squared minus 4 times 3 cubed over 3 plus c. So this will come to 4 equals 3 squared is 9. So 4 times 9 is 36. Minus 4 times 3 cubed is going to be, so 27 times 4 is 108. So it's going to be negative 108 on 3 plus c. 108 on 3 is 36. So 4 equals 36 minus 36 plus c. Therefore, 36 minus 36 just gives you 0. So 4 equals c. So we can't leave our solution like that. You want to find the velocity. So v of t is equal to 4t squared minus 4t cubed on 3 plus 4. So that's your final solution. Average velocity and average acceleration. So the average velocity refers to the change in position or displacement over a certain period of time. So the average velocity can therefore be either positive or negative, depending on the direction of the displacement. So average velocity formula is essentially position 2 minus position 1, so x2 minus x1, divided by time 2 minus time 1. So essentially x2 minus x1 divided by t2 minus t1. Very similar to another formula that you may recall of the gradient. So in this case, we've got an example. A particle moves in a straight line so that its position x centimeters from a fixed point, the origin, on the line at time t seconds is given by the rule x of t equals t squared minus 6t minus 7, where t is an element of 0 to 5. So find the average velocity of this particle over the period of 5 seconds. So average velocity we know is going to be with the formula on the left-hand side. So the first thing you want to do is find x of 5. So that's going to be 5 squared minus 6 times 5 minus 7, which is going to be equal to 25 minus 37, which is equal to negative 12. X of 0 is just going to be 0 squared minus 6 times 0 minus 7, so it's just going to be equal to negative 7. So therefore, putting this into the formula, so average velocity is equal to negative 12 minus negative 7, so it becomes plus 7, over 5 minus 0, so this becomes negative 1 centimeters per second. Average acceleration, on the other hand, refers to the change in velocity over a certain time period. The average acceleration can therefore be either positive or negative, again, depending upon the direction of the displacement. So similar to average velocity in that sense. However, the average acceleration formula, if we notice the difference, is regarding to the velocity of time, or v2 minus v1 divided by t2 minus t1. So the division is the same. However, the numerator, so it's essentially the difference in your velocities rather than your difference in your position. So that's the difference essentially between your average velocity and average acceleration. So let's take a look at this example. So again, in particle moves in a straight line, everything is the same from the previous example. However, now we want to find the average acceleration of this particle over the period of 5 seconds. So the first thing we have to find is the velocity. So well, we know velocity is just equal to the first derivative of x of t. So this is going to be 2t minus 6. So therefore, v of 5 is equal to 2 times 5, which is 10. 10 minus 6 is 4, so it's equals to 4. And therefore, v of 0 is just equal to 2 times 0 is 0, minus 6 is negative 6. Now we can put this into our formula. So average acceleration equals 4 minus 6 over 5 minus 0. So this becomes 4 minus 6 is 10. So 10 over 5, which is equal to 2 centimeters per second squared, because we're looking at average acceleration. So again, just be careful with the units. Average velocity per second, acceleration per second squared. An object's acceleration a in meters per second squared at any time t seconds can be modeled by the function a of t equals 3t squared minus 4t. The object's initial position is 10 units to the right of the origin, and its velocity at this time is equal to 4 meters per second. The function that could model the position of the object can be given by x of t equals t to the power of 4 divided by 4 minus 2t cubed on 3 plus 4t plus 10. Now let's look at this problem in a little bit more detail. So the first thing we want to do is we want to integrate the a of t. So we want to integrate 3t squared minus 4t dt. So this will become 3t cubed on 3, so just t cubed. So this will become v of t is equal to t cubed minus 4t squared on 2 will just become 2t squared plus c. So we know we have the object's initial position, so when time is 0, its velocity is 4 meters per second. So essentially that point tells us v of 0 equals 4. So we can use this point to solve for c. So we have 4 equals 0 cubed minus 2 times 0 squared plus c. Therefore, c equals 4. So now again we can integrate v of t. So x of t will equal the integral of t cubed minus 2t squared plus 4 dt. So this will become t to the power of 4 over 4 minus 2t cubed on 3 plus 4t plus c. Again, we also have this information. So x of 0 equals 10. So it's to the right of the origin, so it's positive 10. So now we can substitute this in and solve for c. So we have 10 is equal to 0 to the power of 4 on 4 minus 2 times 0 to the power of 3 on 3 plus 4 times 0 and then plus c. So therefore, c is equal to 10. And to write our final solution, we have x of t is equal to t to the power of 4 over 4 minus 2t cubed on 3 plus 4t plus 10. So in summary, position, velocity, and acceleration. To move from the position, we derive to get the velocity, then we derive that to get the acceleration. Then to go from acceleration to velocity, we integrate once, and then to go from velocity to position, we integrate again. Average velocity and average acceleration. The average velocity essentially is your change in position with respect to time, and your average acceleration is your change in velocity with respect to time. For distance and displacement, distance refers to the sum of the y values, regardless of the sign, so it doesn't matter whether they're positive or negative, you're adding those distances together, whereas displacement refers to the sum of the y values inclusive of a sign. So essentially, if you started at 126 and then you finished at 126, displacement would be 0. In our next lesson, we are starting to look at the chapter 11 chapter checks.